This is Kelly Hill from RCR Wireless News. Welcome to today's webinar on making interference hunting easier. We're joined by Eric Hakanson and Steve Thomas, both Senior Product Managers at Anritsu. This webinar will be archived on RCR Wireless's YouTube channel, and we will have a question and answer session after the slide presentation, so please submit your questions at any point during the webinar. And right now, we'll get started with the presentation on interference hunting. Steve, why don't you go ahead and start us off?
Thank you, Kelly. This is Steve Thomas, and today I'm also joined by Eric Hakanson. We're both Senior Product Managers at Anritsu, and I think what we're going to present today you'll find very useful. What we're going to work on is how to find interference. What is interference? We're going to talk about a step-by-step process to find different types of interference, and at the end we'll discuss tools to make the job of finding interference easier. And as Kelly said, we'll have Q&A. Feel free to enter questions at any time during the presentation, and we will look through the questions and answer the ones that we can. First, what is interference? Basically, it's anything that makes a radio receiver's job harder. It might be local received noise, electromagnetic interference, multipath that's messing up the quality of the signal, even other radios on the same frequency, near the same frequency, or with enough power to cause fundamental overload. And interference can be caused by basically anything that carries or uses electricity. It might be other radios in the same system or other systems. It might be all kinds of unlicensed things. I've shown some of them here. It might be jammers. They really exist. We'll show pictures of some later on. Repeaters of various sorts, especially including cell phone boosters, because they can cause all kinds of nasty, hard-to-solve problems. Leakage from cable TV installations. Light ballast for fluorescent tubes will do really interesting things and generate signals. The power system, the power grid, can cause all kinds of interesting trouble. There's a fellow I know whose specialty is tracking down those problems, and he travels all over the country doing so. Heaters, lighting control systems, anything digital. I know of a hospital that had lots of trouble with interference. It turned out to be caused by the controller for an elevator. Lots and lots of fun. So what we're going to do now is go through the how to find interference, the step-by-step process. And for this part, I'm going to turn the mic over to Eric Hakanson, who will take it from here.
Thank you, Steve. So we've got a 5-step process we're going to talk about. Let's do a quick overview first. First thing is know that you've got a problem, know that it exists. See what it looks like on a spectrum analyzer. That's really helpful for knowing when you've actually found something. But you want to do that near where the radio receiver is being affected. Then we need to estimate the position of the emitter so we have an idea of where to go. Travel to that position, and then refine the estimate till the emitter is found. Sounds really simple, right? Well, there's a bunch of details that we'll go through. So starting with know that it exists. And that's kind of the philosophy, if it ain't broke, don't fix it. We'll talk about other philosophies in a moment, but let's talk about this one first. And there are various methods. We'll go through each of these. We can do a survey. We can use to see what's going on in the spectrum. We can get complaints from users. We can do error rate measurements, especially on point-to-point radios. We can get some indication that the throughput is reduced through a network. And in cellular phone systems, they have a very powerful tool called switch statistics that can tell all kinds of things about what's going on. Or, and I say with a question mark here, proactive fixes. And people don't do this very much, but I think they're starting to do it a little bit more. Starting with spectrum clearing. When there's an auction and spectrum is refarmed from one use to another, the old users are often still around. So people go around and find out what's still there. And maybe go to places where you know there are problems. Wireless microphones are another common cause of interference. Stadiums, theaters, karaoke bars, churches all use these, and they may be using the wrong frequencies, or they may be emitting things that they shouldn't. And another interesting case is new construction of large buildings. Somebody who's really concerned about interference might go there and see what they're using for lighting and ballasts, because those can cause very hard to solve problems, especially after the building is put in. Step 2, see what it looks like on a spectrum analyzer. And this makes it it's really informative about what's going on. We think it's absolutely key, so you know what you're hunting for. Some signals are easy to see, others are much harder. We have a number of examples of those later with some screenshots that'll, I think, be very instructive. It's also useful to capture this as a reference trace. So when you go out and find the interfering signal, you can say, oh yeah, that was really the thing that I saw when I was back at the location where the radio was affected, like a base station. And then we're going to talk about where to look to get a reference point for this. So some hints along with this when we're spotting interference in the field is start at, say, the base station where the affected radio is, and take a look at the spectrum and see what belongs. It means you need some experience with what the correct signal is supposed to look like, and then mentally remove that and see what's left and what doesn't belong, and that's your interference. And that's very powerful. That's why we think it's key to look at the spectrum with a spectrum analyzer. And then it's a good idea to measure the noise floor using a receive antenna. Ideally, the same antenna as the radio, if there's a test port, or something with a similar pattern. And check the receive channel power. That should be the same as a noise floor number from switch statistics, if you've got those. And if you can, use the same filter or a similar filter to eliminate signals the receiver doesn't care about. If not possible, you can mentally ignore those. But it's better to have a filter to get rid of them in case there are intermods that come up from those signals. And then, as we talked about, know what you're looking for. Get a visual idea on the interfering signal. But you can use some extra information there, like what's the bandwidth, what does it look like, what's the modulation type, capture the reference trace like we mentioned. But you could also demodulate it if it's, say, analog AM or FM. Sometimes you get a signal ID, and that can be a wonderful clue about where it's coming from. One of the tools here is to use max hold on a spectrum analyzer. And we're looking at two traces here, one of which is a bursty signal. It's an LTE uplink with a CW signal in the guard band. And the max hold shows both of those going on. You can see the little signal sticking out of the max hold on the left as well as the current trace. So that's a good reference point. Helps you know what's going on. So let's talk about some of those examples. We'll start with easy cases. That one I was just talking about is particularly easy, where there's a CW signal that's in the guard band where there's kind of no other signal around. Those are particularly easy to see. It could be a wireless microphone, for example. And I've even run into a case where we've had an interfering signal where the wireless microphone was turned off. I don't think that was very good for battery life. Clearly not a very good design. Another common case here is an oscillating repeater or a signal booster, especially the older models that don't turn themselves off when they detect oscillation. This isn't quite CW because the signal often drifts around, but it's very CW-like. Now let's look at some harder to see signals. Broadband noise or noise-like signals like jammers. There's a picture of a jammer off the internet. Fluorescent lighting ballasts, they can create quite a bit of noise, which can be quite problematic, especially if there are thousands of them installed in a building. And cable TV is not noise, but it's noise-like because it's a broadband spectrum. A good way to see these is to look in the guard band between allocated channels where there's not supposed to be anything, and then change the antenna direction. If you've got a directional antenna, say, okay, in one direction I see a lot of signal where it shouldn't be, and in another direction there's nothing. So I know there's really energy that's not supposed to be there. Another way to do that is just disconnect the antenna. You don't get the bearing, and you don't get maybe other things in the receive channel like a tower-mounted amplifier, but that's still quite useful. And then again, as I mentioned before, make a reference trace so you can see what it looks like when you're out in the field. And as we mentioned, notice the spectrum shape. And the picture we see there is from cable TV leakage. One thing to do with broadband noise-like signals is to use trace averaging or narrow video bandwidth. to get the shape of the signal and not be distracted by the noise aspects of it. And you can see on that signal there are very clear channel boundaries. There's dips in the signal about every 6 megahertz, just like cable TV. That's a good signature of cable TV signals. Some other harder to see interference signals is a CW signal that's underneath the transmit channel. It's at the same frequency, so the transmit channel is hiding the CW signal. One way to deal with that is use narrow resolution bandwidth, because the modulated signal level drops, but the CW signal doesn't. The limitation of that is it can be pretty slow. But if you have a bursty signal, like is pretty common for uplink on many cell systems, is use min-hold. That when the burst goes away, the CW signal is still there. And I've mentioned uplink a couple of times. That tends to be where the most interference problems happen, because when there's a problem, it takes out an entire cell site sector rather than maybe just one phone. So it has much bigger impact. So that tends to be what people focus on. Let's talk a little bit more about min-hold. There's a nice picture here that shows 3 traces. The yellow trace is live, and I happened to catch one there when the cell phone was transmitting. Pretty hard to see that signal down on the marker when that cell phone is on, especially when it's jumping around. The max hold, like we talked about before, shows where everything is jumping around as a reference. But the trace C, the blue, is min-hold. When all of the radios aren't transmitting, you still see that CW signal there. That's a really good tool for finding those small CW signals, or even other types of signals when the radio is turned off. Now we're going to move into very hard to see interfering signals. This is where it takes a fair amount of skill to see what's going on. You might want to pay special attention here. So transients, these are tough, and it's always true. Things that come and go are always more difficult. So for example, the newer types of repeaters, that when they detect oscillation, they turn themselves off, and then they wait a while and turn themselves back on again. Reduces the amount of interference, but it makes the job of the person finding it that much harder. Or a repeater on a boat, that maybe when it's at one position or one angle, it oscillates because there's bad isolation, but then the boat moves, which happens quite often, the isolation changes and the signal goes away. Or bursty transmitters. There's a number of these, things that are very low power for saving their battery, or things that only transmit, say, once a day, such as uplinks of data from point-of-sale systems, or keyed transmitters that only transmit when a person is holding a key down, or even worse, when you get intermodulation from multiple keyed transmitters. So you only get the signal when several transmitters are on at the same time. That's particularly difficult. Jammers in schools or churches, maybe they're only on at particular times of the day or week. Drifting signals, those aren't quite as bad, but there can be a bit of a pain to tune to, and you have to kind of keep track of where they are as you're looking for them. Or signals that are physically moving, like a jammer in a car or in someone's pocket. Those can be a real pain, because as you're looking for them, suddenly they're in a different place. Or they're cell phone boosters or repeaters in boats or trucks, things that are moving all the time. Those, again, can be particularly difficult. But we have a bunch of tools to help with that, starting with a spectrogram. So this is kind of a spectrum on steroids that shows not just frequency and amplitude, but also adds the additional dimension of time. The picture we're looking at there in the upper left corner has a regular spectrum trace on the bottom, but the top is the spectrogram. That has frequency on the x-axis again, but now time on the y-axis. And to get amplitude, we use color. So we can see the signal drifting around over in frequency, over on the right third of the display, and get a good indication of what the amplitude is. Another tool is called Save on Event, where we can do a mask of a signal we're expecting using a feature called Auto Mask. And then when the amplitude of the signal exceeds or goes below even that mask, we can automatically record that on mass media. So that's particularly good for rare signals. Maybe something that's too long a time for a spectrogram, over many, many days, for example. Or you just want to compress things rather than having to wade through a bunch of parts of the signal that you don't really care about. And then a third tool is something called burst detect, which is kind of like MaxHold, but it works really fast. Runs about 10 kilohertz, so we can capture signals as small as 200 microseconds. And then draws the trace and then resets. So this is helpful that you can see the dynamics of a signal over time, for example, as you're moving an antenna, but you also can capture very small bursts. So this is a really good tool. And then on top of that, you can combine that with a spectrogram or save-on event. A little bit more on a spectrogram. It can be a fairly short view, seconds to minutes, if there's something drifting around, for example, or it can be a very long-term view. You can get days of recording time for this that you can look at on screen, compressed in time, or you can record this to mass media and look at it in detail on a separate PC. You can also have the compression using MaxHold or MinHold if that's a useful tool. So there's a lot of good stuff there. A little bit more on save on event, where we're automatically recording traces when the mask is exceeded, or we can just record every event if we want to have lots of detail recorded in mass memory. We can recall those traces and look at them and look at the timestamp, for example, or we can view those as a spectrogram. We can take those into a PC using master software tools and show that even in normal 2 dimensions or 3 dimensions, or replay it as a video file. Okay, we talked about needing to do these first measurements near the radio receiver being affected. Let's talk about that in a little more detail. A good place to do that is the test port on an antenna feed, like the picture on the bottom there. It's probably the best possible location, especially if there's a tower-mounted amplifier, because you have a good high-gain antenna that's up out of the clutter with good noise figure. Second best place would be on a rooftop, or maybe a parking garage, a particularly convenient rooftop to get to, using an omnidirectional or directional antenna. Directional antenna will have higher gain and give you an indication of where the source is coming from. Or third choice would be at ground level, with again a directional or omnidirectional antenna. And if you have an antenna mast that you can raise up, that'll help again get out of the clutter, or if not, at ground level. Okay, now on to step 3. We've seen the spectrum at a known location. We want to do an estimate of where the emitter is located. So we use a directional antenna. It could be like in a cellular network, a particular sector. And we can even get amplitude from adjacent cells, either in the same physical location or in another location. And we can use those to get a pretty good estimate. If we just have a bearing, we know what way to go. If we have multiple pieces of information, we even have a distance estimate. Some hints about spotting the signal at ground level. Again, when we have a signal at the tower, we're looking at the tower, we can have a high gain antenna with good noise figure. Maybe we can see the signal there, but we can't see it at ground level because of all the clutter you can get. So some hints. Just like we talked about, check adjacent sectors for the interfering signal strength. That can give you a rough idea of bearing. Or even from a different cell, you can get a relative signal level and maybe a rough idea of the distance between the cells. And then when you've got that rough estimate, drive around a little bit and be looking at the amplitude as you're driving around. An omni antenna that's maybe mag-mounted on your roof can be really helpful for that. Maybe, as we talked about before, MaxHold and MinHold, MaxHold and normal traces, and maybe even MinHold for something that's bursty. And the coverage mapping tool that we have in our instruments can be helpful for that too, to keep track. Mentioned using a building top or an open area for direction finding. That can be really useful too. So step 4, pretty simple. Travel to the estimated position. Walk, run, drive, use a train, whatever. Now that we're close to the emitter, we refine our estimate. And this is where things get a little more complicated. We've figured out ways to capture difficult signals, but how do we refine our estimate given that we're relatively near? And there's several techniques for that. We'll talk about each of these: survey, triangulation, and successive approximation. Each of these have trade-offs, and they can be maybe optimally used in slightly different conditions. Then we'll talk about the real world, which is usually a combination of those. So a survey, if I, in a place where I don't get a good bearing, basically just drive around and keep track of signal amplitude. And we have a picture here from our coverage mapping capability. This happens to be an indoor case, but that's also useful for finding signal emitters indoors in complicated situations. So basically you drive around, record the amplitude, go back to where the biggest amplitude is, and refine from there. It's very effective. Unfortunately, it can be slow. That's the biggest trade-off of this technique. The second technique is triangulation, where we can take multiple bearings. You can see on our map here, you have 3 bearings all pointing to the same location, a pretty good indication of where the emitter is coming from. So travel to the estimated position and then repeat, and you can refine your estimate as you go along. This generally works where you have clear line of sight or near line of sight to the signal because the bearing estimates can be confused by multipath. Moving half a wavelength can help average out the multipath. Having many bearings can also help. This can be the fastest technique, especially where there are clear bearings and there's a relatively long distance to the emitter. It's also, I should have mentioned in the slide, also gives you the most confidence because if you know it's in a direction, you can see it. Some techniques for this is once you've gotten the bearing, if you can shield the antenna from that bearing and the signal goes down, you have a very good idea that yes, the signal is really in that direction. So I'll move behind a building or another vehicle. Some spectrum analyzer tools for this. Again, dual trace mode, where you can keep track of the highest amplitude as well as the current amplitude. Maybe min-hold again, too. A signal strength meter, just as a visual and audible display of the amplitude of the signal. Or interference mapping that has a visual and audible display as well. And then the third technique is successive approximation, which is also known as homing, where you take a bearing to the emitter, just travel along that bearing line until the bearing changes, and change direction, and keep doing that till you're led to yourself. You're led to the emitter source. This can be fooled by severe reflections, although much less than the triangulation method. It also can be very fast, especially when there's lots of multipath and short distance to emitter. So a particularly good case for this is when you're in a city with tall buildings, where maybe you only have multipath. There maybe is no line of sight. And so instead of getting fooled by the urban canyons, maybe we can use them to help find the emitter. So when you get to an intersection, as the picture on the left shows, you have several directions you could go. Measure the signal strength in each direction, and then whichever is biggest, go in that direction. That's a very good indication of where the emitter is coming from. Eventually, as you pass the emitter, the direction of arrival will change dramatically, which means you're very close. And then you can use traditional direction finding techniques to find the actual source. Once you are close, maybe you're out of your vehicle, for example, you know it's very close to where you are, start looking around for potential sources. Things you know can cause interference. Look for antennas, especially older ones. Look for radios. Look for rust that might be causing intermodulation. So, for example, a rusty fence. Look for buildings, homes or businesses. Look for cell phone jammers. If you've got one of those sitting somewhere, that's a really good sign. Make sure you keep your eyes open. Look in all directions, up, down, and all around. It's easy to forget. I was looking for a signal a few weeks ago, and it's like around here somewhere, looking up, and then we looked down and discovered a cable TV box, and sure enough, that's where the signal was coming from. And using your directional antenna or even the Omni to locate the emitter is very helpful here. Bigger power as you get closer. And then the real-world technique is usually a combination of all of those. For example, you start from the cellular base station and do rough triangulation. Then you do a survey in that rough location to find the general area. And maybe there's a set of buildings in a strip mall, for example. And you might use triangulation to find the building, and then you use successive approximation to find the device. Or you can mix and match other ways depending on particular situations. But that's, I think, a pretty good example. Okay, that's the process. We'll now have Steve talk about tools to make the job easier. Steve?
Thank you, Eric. That was good. With our instruments, we have an interference analysis option that's very handy because it allows you to see the spectrogram. It allows you to do interference hunting in a lot of effective ways. We offer numerous directional antennas, some broadband, some relatively narrowband Yagis. You can mix and match and choose the ones that you need, and basically help make your life easier. And we have a number of accessories that we've introduced. The middle picture on the bottom is a device we call a handheld interference hunter. And we'll talk about that more. We have we're working on a case so you can put that and a whole flock of antennas in. So depending on where you need to go to and frequencies you need to cover, you can have just what you need in the case. Yeah, that's what I wanted. Now, I mentioned the spectrogram. You can get time added to the spectrum, and this is really useful for things that are intermittent. Notice in the picture on the upper left, there's little red places right in the middle of the frequency range. Those are signals that popped up intermittently, and they were very strong. This red's a strong signal. That would be easy to miss if you don't have this view showing time. The signal strength meter, you can turn on a tone, so you can be aiming your directional antenna and listening for the highest signal level. It makes very handy for successive approximation or direction finding. Receive signal strength indication shows you intermittent signal timing and also signals that drift over time. But especially for intermittent signals, we show narrow pulse that pops up occasionally, and that would be hard to see without burst detect, which we'll talk about as well. And then in-instrument mapping to help you triangulate the interfering signal. With the various directional antennas that can be attached to the instrument, you have some easy tools for getting the exact coverage you need over the frequency range you need. And if you're doing something really broad, you can choose some of the log periodic antennas. If you're doing narrower things, channelized work, you can choose the higher gain Yagi antennas. The accessories, the preamplifiers are sometimes useful accessories to improve the ability to see small signals. You need a GPS receiver so you know where you are, especially for mapping, and an electronic compass to get to where you are. The antenna holder we've been talking about, this Anritsu MA2700, we call handheld interference hunter, includes all of those items, preamp, GPS, electronic compass, in a single ergonomic, easy-to-use package. Plus, you have the option of attaching bandpass filters right at the antenna before the preamplifier to help eliminate big signals that are going to that could potentially cause problems for the receiver. And to make life simple, you can add a tripod or a monopod. The monopod is really handy. It doesn't take up much space. You can make it long enough that you can put the antenna up in the air, away from some ground clutter. We have all kinds of cables available to hook up what you need to hook up, and transit cases both for the interference hunter and antennas as well as the instruments. Here's a closer picture of the interference hunter. You can see a trigger on the handle. You squeeze that, quick squeeze, and it will save the location and bearing data on the on-screen map. You can see the crossed lines, the orange-colored lines. Those are the bearings. So take measurements over a wide range of location, and unless you've been seriously fooled by multipath, you'll get crossed bearings and be able to get a good position estimate and go continue the process that Eric talked about. Now, we have all kinds of resources available to help you do your job. Application notes, a bunch of videos, archived webinars such as this one, and classes on how to do interference hiding, how to use spectrum analyzers, and all kinds of other interesting topics. And there's a link there that you could actually go to see the interference analysis class. I mentioned we have a number of application notes on direction finding and finding hidden signals and just all kinds of things to help you do your job. And numerous videos showing how to use the tools to make your life easier, make interference hiding easier. Those are located on the Anritsu site, and a lot of them are also on YouTube. So there's some other some things we did earlier, finding hidden transmitters. We did in 2011. Finding interferers also in 2011. Easy map tools in 2013. There's all kinds of webinar resources to help you learn what you need to learn to be effective at your job. The interference hunting class is a really good way to also get you up to speed. This is just the agenda for that class. And, there's 7 lectures and 5 labs to get you up to speed, get you started doing knowing what you need to know. So one of the things that we do know is that interference is a large and growing problem. I was curious, so I went to the FCC database to see how many transmitters were within a mile of the Anritsu location in Morgan Hill, California. And within a mile, there's 521 licensed transmitters. And I say that's a growing number because when I looked at the same information 2 years ago, it was something like 244. So it's growing rapidly. And that doesn't include all the unlicensed stuff, the profusion of Wi-Fi access points, microwave ovens, baby monitors, all kinds of things. And the step-by-step process that Eric detailed will go a long way helping you be effective in finding and solving interference problems. And there are lots of tools available to help you do that. Now, we are planning to do more webinars in the near future on interference hunting topics. So what else would you like to know? And just to get you started, we've listed some potential topics here. But if you have something that you particularly like, go ahead and send an email to me, steve.thomas@anritsu.com, giving your ideas and desires and what would help you be more effective, and we will start cranking those things into future webinars. What ended up happening, by the way, was as we were creating this webinar, we ended up with way too much material. And so we said, you know, we've got enough that we could talk for 3 hours, but people aren't going to stick around. So we honed it down some. But we'd like to talk about some other topics if you're interested, so let us know. Now, I see some of you have been sending questions along, so go ahead and do that now. And you can also send questions to me to be answered after the webinar. A PDF version of these slides will be made available after the webinar, and RCR will have the archived webinar in a few days after this broadcast is finished. Let me go back. So if you I put the future slide on here, so if you have, this to give you an idea, if you have things you'd like to know about, let us know.
Okay, great. Steve, thanks so much. Audience, now we are going to get into the Q&A portion, so if you do have questions, please submit those. We do have a few already, and our first question is how MIMO will support this kind of antennas. So getting into the topic of MIMO and how that affects what's going on here.
Okay, we'll have Eric answer that question.
Yes, that's an interesting question. There's a lot of confusion about MIMO. It really is using multiple transmit antennas and possibly multiple receive antennas. And the simple answer to that is it has no effect at all, because in general the transmit and receive antennas are both very close to each other, and the effect of the interference on both of them is essentially identical. So, for example, if you have a situation with one transmit and two receives, you might want to pick the test port on the one receive to make sure there's no leakage from the downlink signal. But other than that, there's nothing to worry about.
Okay. We also have a question of could it be helpful to use LNA in most cases?
Well, yes, it can be. A low noise amplifier can sometimes improve the noise floor enough that signals that are low or non-visible at ground level might be made visible. Often you don't need it, but sometimes they can be helpful.
Let me amplify that just a little bit, Steve.
Okay.
A couple other things related to that is directional antennas also have gain, which is there's nothing better than having a lot of signal to begin with, so that's great. There's a downside to an LNA too, that the gain there can actually overload the spectrum analyzer if you have a large signal. So being able to turn it off is really helpful. And Steve was talking about the interference hunter, MA2700A earlier, which has a preamplifier in it. You can also turn it off. In fact, if you hold that trigger down for 2 seconds, it will toggle the preamp on and off, just to make that convenient.
And I've also been in situations where I was helping a cell phone provider hunt for interference. And this was in an urban canyon, and as we walked past some other base station, other than the provider I was helping that day, the preamplifier would have been just no help at all, because even without the preamplifier, we were causing mixer saturation in the spectrum analyzer, and a bandpass filter was needed to eliminate that.
Yeah, that's a good point, Steve. Having a set of filters available to eliminate large downlink signals when you're looking for interference in the uplink can be really helpful.
Okay. Another audience question. Sometimes interference comes from 2 different directions, and that happened to me. Any suggestions on dealing with that?
That's a really good point. And normally, or most commonly, you have just one signal and it's really easy to find. But when you have 2, you can get really fooled. You're looking in one direction and you have a large signal. You're looking in another direction and, wait a minute, I have a large signal there too. So one technique is keep following, find one, eliminate it. And we actually should have put another step in here, is go back and verify that you actually eliminated the interference at the base station. So if you find an interferer, you go back and, wait a minute, there's still a signal there. How can that be? Oh, there must be another emitter. So you repeat the process. Another way to do this is, as you're taking bearings, if you take enough of them, you may discover that there are 2 crossing points. Oh, there's an emitter over here, there's an emitter over in this other location. Now, I got to be careful. Sometimes that's not really an emitter. Maybe it's a hill that's reflecting the signal. You can get fooled by that. Or you can be behind a building. We actually have used this in some of our training classes. You go behind a building and you see the signal from the hill, but you don't see the signal from the transmitter. So be aware that those situations do exist. I think multipath is far more common, but the multiple emitter case definitely can exist.
Yeah, in fact, I ran across one of those where somebody put a bunch of little jamming transmitters near a repeater, and it was tedious. It took a long time, but we just had to find them and eliminate them one at a time. And some of them were up in trees. It was just, it was a nasty situation, and it's not easy. But you just find what you can find and then go for the next one. You know, you're not going to find both of them at once. You're only going to find one at a time.
Okay. Another audience question. During a major event like the Olympics, we may have lots and lots of wireless mics, cameras, etc. How do you measure interference over these elements in this very crowded environment?
That's a really interesting question, and the National Football League actually dealt with that forthrightly a few years ago by equipping every NFL stadium with a spectrum analyzer and a person trained to use it. And they end up with the authority to coordinate the operating frequencies of all the various spectrum users. And you know, in a traditional, typical Sunday NFL football game, there are about 500 emitters in the stadium, and that number goes up to over 1,000 during Super Bowl. And it's, you know, you can't find and fix the interference during the event if you haven't coordinated things in advance. If you've coordinated it, it's mostly running smoothly. You only have to deal with the corner cases of some reporter who showed up at the last minute because it was a last-minute assignment and his mic wasn't coordinated and it's stepping on somebody else. Those you can deal with. But if it's the Wild West and everybody does what they want, I ran into that up in Seattle one time where there's a venue near the Space Needle that holds all kinds of events, and they'll have multiple bands with multiple wireless microphone sets, and it was horrible. It was a Wild West situation where nobody was in charge, and nobody had taken the authority to say, look, you've got to coordinate your frequencies with us. So it's a hard one. It really is a hard one, but you have to deal with it in advance. Otherwise, you're dead.
Maybe to amplify a little bit there, Olympics is maybe even worse than an NFL situation because of so many things going on. It might be handy to have multiple people available, and coordinating between two people looking for an emitter can make the process faster. For example, if you can take two bearings with two people, you can do that all at once rather than having to travel between the locations.
Okay. This was something that Eric mentioned during his part of the presentation, and I'm wondering if you two could tell us a little bit more about switch statistics and whether they're enough to find the source of interference?
That's a great question, and I've actually met a number of RF performance engineers that think it is, but then they have never actually gone out and found the emitter. They're a great tool to get started. They tell you that there's a problem, that there's blocked signals, blocked phone calls at a site. They tell you what time of day. They can give you indications of the signal level. I've even seen some recent tools that give you a rough picture of the spectrum by looking at in an LTE signal the power versus the resource block over time. But it's not the same as looking at the spectrum, and it's not the same as getting in your car and going out and actually finding it. So I would say it's a great tool, but it's not the only tool.
Okay. Steve, anything to add?
No, I think that pretty well covered the waterfront on that.
Okay, great. Another audience question about a study case. We have an in-building system for a cellular system in 850 megahertz, and we make interference with infrared sensors in the building installation, and there are sensor malfunctions. Any recommendations for that specific case?
Well, I think that's another great example of how anything that has electricity in it can cause interference. And it's not just radios, it's not just repeaters, anything that has electricity in it. So the infrared sensor, you think, oh, it's infrared, there's no RF. Well, it has a clock in it because it's digital, and that clock has harmonics, and those things transmit. I was at talking with an RF performance engineer a few weeks ago, and he said, oh yeah, we've got these systems that work at 300 megahertz, they're not a problem, except the third harmonic of the clock just happens to be in our uplink. So we talked to the people, and they had a new firmware download, and they moved the clock frequency a little bit, and the interference went away.
Okay. You showed pictures with a map on the instrument display. How do you get the map into the instrument?
Oh, that's a good question. We have a piece of software that we provide that's downloadable from our website called Easy Map Tools. And you can use it to get maps from basically anywhere in the world where there are roads and convert them into a format. And there are two formats. There's a map format, .map, and a .azm format, which stands for Anritsu Zoomable Map. And you can say, I want to cover this whole area, and I want to cover this whole area with this level of detail, and then it will generate the map or maps needed to cover that area. And then you stick them on a USB stick and copy them into the instrument. And it's fairly straightforward, not hard to do. You get to name them whatever you want to name them, and it makes life simple because you can see where you are on the map. Now, you can actually DF without maps. You have this gray screen, which isn't very interesting to look at. You have to pay attention to where you are, but even without maps, it still is functional.
Great. And Eric, this was another thing that was mentioned in your presentation about burst detect. Is that the same as real time? And if not, what's the difference?
I like to call that a poor man's real time. Real time gives you all of the spectrums. Basically, the FFT rate is so fast that you never miss anything. And burst detect is kind of like that, but it doesn't show you each individual spectrum. It takes that max hold over some period of time, like 100 milliseconds or a few seconds or whatever you choose, and then shows you that picture and resets and starts. So it's maybe enough like real-time that you don't need a real-time analyzer for many cases, although real-time analyzers, which are very expensive, can be used for specific cases when you need to have even more information.
Okay. Another audience question, will you plan a webinar for interference hunting for HetNet networks? Definitely a topic on trend.
Yeah, that's referring to basically using small cells along with big cells. HetNet stands for heterogeneous networks that basically have different cell types. And we'll take that as a suggestion. I think that's a really good one to have some focused points on the specific situations that can happen when you're using small cells.
Okay, we just got another question on the map. Is there any way on the map page to zoom in and out without having to load a new picture of the map with the zoom you want?
The answer is yes and no. Part of it depends on the firmware revision in your instrument. But if you have a sufficiently advanced firmware, and some of our products have it, other ones will soon, you can load in a zoomable map, which is basically a whole flock of tiles that show the level of detail that you want, and then you can zoom in to the area of the map that you're particularly interested in. Okay, that wasn't very good. Apparently, my mic was good. Was that hearable?
No.
No. Okay.
Can you? Yeah. Why don't you go ahead and repeat that answer, Steve, just so that we can make sure everybody gets that.
Okay. Sorry about that. Yes and no. You can, with some of our instruments, you can have a zoomable map in the instrument, which allows you to have whatever coverage area you want, and then zoom in to the area that you need to without having to load additional maps. Other older firmware will only have maps at a single resolution. But we're going to the zoomable maps on everything. So pretty soon that won't be an issue at all. And you can cover, let's say, a metro area with street level detail in a single download into the instrument. I did have somebody ask a few weeks ago whether we can cover the entire country of Brazil with street level maps. And the answer was, it gets pretty big. That choose the urban area that you're in and use a map for that area. I was messing with it, and let's say Denver or Washington, D.C. or San Francisco, and I've done all these, the ones where you can get the whole city and surrounding areas to street level detail and not have it be too big.
And you could also have multiple maps in the instrument or on an external USB stick. You can have many, many, many maps to be able to cover very large areas if you want to do that.
Yep, and just to make that point a little, to drive it home, you can actually use the maps right off the USB stick. You don't have to download them into the instrument.
Okay. There were several different types of antennas mentioned. I'm wondering if you folks could talk about what kind of antenna is best for finding interfering signals.
Yeah, that's a really interesting question, and the answer is it depends. You know, I think that's a wonderful answer because it's the truth. If I'm looking at a relatively narrow frequency range, a Yagi antenna is probably a best choice for being able to direction find on the signal because you have great front to back ratio and excellent gain and very smooth side lobe performance. But if you need to work over a wider frequency range, a log periodic antenna can be very helpful. They have good front to back ratio. They're not as good as a Yagi, and they'll cover a wide range. Let's say we have one that we offer that's 1 to 18 gigahertz in a single antenna, and it's just very handy to have just one item when you're doing wide range of frequency measurements. And there's even places for omnidirectional antennas. If you're in a restricted area, for example, or where it's tight space-wise, where you can't bring a Yagi antenna in because it's too big, you can use successive approximation with an omnidirectional antenna. I've done that myself, driving into an area and just had the spectrum analyzer on the seat and antenna either on the instrument or on the roof, and you just drive as the signal gets bigger. So you just and then once you get close, you probably want to switch to a directional antenna just to make life a little quicker.
Kind of like that old children's game of hotter, 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 colder, 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 right?
Exactly right. That's exactly what it is.
Okay, another audience question. Is the tool also a power meter? If the accuracy for RSSI measurement is high, can we translate it into power received with the same accuracy?
It's with the spectrum analyzer, you do not generally get power meter accuracy. You'll get fractional to 1 dB accuracies with the spectrum analyzer, and for interference hunting, that's plenty. That's plenty good, because you don't really give a rat's ass what the exact power is. It's just causing interference. So you want to get rid of it, whether it's 42.6 dB per hertz or 48.1. It doesn't matter.
With one exception, however, when you're making a complaint to the FCC or other regulatory body, you may need to know what the field strength is. And their accuracy is pretty important. But again, because of things like multipath and exact antenna placement, it's hard to get more than many tenths of a dB accuracy coming into the analyzer. So anything better than fractional dB accuracy in the analyzer is of no value whatsoever.
Okay. Another audience question: do you have any plans to depict the interference management in HetNet as EICIC and ICIC?
So that's an interesting question because it's a completely different kind of interference. We've been talking about mostly external interference that's not caused by your own network. Mm-hmm. Those terms, ICIC and EICIC, are intercell interference cancellation and enhanced intercell interference cancellation, or coordination. So that's really part of the network, not part of finding an external transmitter. So that's something that we may consider adding as part of our interference portfolio, but it's not something we've looked at this point. And it's not part of this seminar.
Okay. Great. Well, that wraps up our time today. Eric and Steve, thank you for lending your expertise to the discussion, and thank you to our audience for joining us today. Again, this presentation will be archived on the RCR Wireless YouTube channel for later reference. This concludes the webinar.